Okay. Okay, so here we go. So this one will be a second lecture about many-body perturbation theory. So it's a direct follow-up of what Daniele explained in the morning. So there is basically a second step. Daniele told you, gave you the introduction, and then told you how we perform in general many-body calculation to compute quasi-particle corrections to the DFT energies, the so-called GW method. But then he also mentioned this is still not enough, this is yet not enough in some cases to reproduce spectroscopic observables, such as optical absorption spectra and the related ones, such as reflectance, transmittance, and also others, such as electron energy loss spectra, and so on. This is still a many-body problem, but we didn't completely solve it with the previous lecture, and now we will see how we try to describe what are called neutral excitations, neutral electronic excitations. Okay, so I come from the same place as Daniele, Modena, Nanoscience Institute. Just if you don't know, I prepared some introductory slides. Modena is in northern Italy and in the Po Valley. And if we zoom into northern Italy, okay. So this is Modena in the center. You see we are basically 2 hours by high-speed train from Milan and from Venice, and directly be on the other side of the mountains with respect to Florence, right? So this is our location, this is our Tower Bell, and that's it. And also, this is, I hope, okay. This is a picture of the latest school. This was a specific school about the Yambo code and about many-body calculation that we had in Modena last year. And so this is me, Daniele is here, all the other developers and the participants. Okay, so what is now our interest? What do we want to calculate? Well, this type of processes. Let's look at the one on the top line. So this is optical absorption. Some electromagnetic waves, for example, from a laser, they impinge on our material. And then we measure the either transmitted or reflected wave, which will not be the same anymore as the initial one, because some part of the wave, some frequencies in which we can describe the electromagnetic wave, have been absorbed with different intensities by the system. So typically, what we can obtain is an optical absorption spectrum that has peaks at several energies, okay, that mark where there is the most absorption in the frequency range of the incoming light, right? And the fact that here you have isolated peaks is really a hallmark of the quantum nature of the system that microscopically hides inside the material. Another process is emission. For example, luminescence. In this case, we directly generate some electronic excitation inside the system because of the absorbed light, but then we wait for the system to relax to the ground state, and then light has to be emitted again. This can also be detected, giving rise to a different spectral feature, and this is called luminescence, right? But they are very linked, as you see, very similar. Okay, but what is the microscopic origin of this? What gives the details of this absorption spectrum? As Daniel explained before, we have to consider the crystal structure of the system, how the electrons are organized, and their energy landscape. This is a band structure, an electronic band structure that give you the dispersion of the electronic energies in a reciprocal space. And the absorption process, the absorption phenomenon, is the fact that an electron that in the ground state sits in what is called the valence band absorbs a photon of the correct energy to jump at an energy level that it wasn't occupying before. This is called the conduction band. And so we have the electron goes here and leaves behind, let's say, a vacancy of where it used to be before, that has an effective positive charge. Imagine that you have an organization of electrons in your system, then one electron moves, what remains there with respect to the ground state is a kind of effective positive charge. And this we call usually the hole. So these are understood as electron-hole transitions, okay? Since the hole has a positive charge and the electron has a negative charge, these two are not independent, and in principle, they can feel each other through electrostatic interaction, right? And this is where we will go in the next slides. Why this is very important? This is what I said before. So the details of the absorption process are given by the underlying microscopic structure of the material. And this is where we have to go. But to go to the microscopic regime, then we need to switch to quantum mechanics, as Daniele explained at the beginning of his lecture. Here we have a crystal structure, and then we have the electron density that is organized not uniformly, but around the crystal structure. So this is what we want to describe. Okay, so why? This is a very famous picture. So probably you know very well that since 20 years, there is a very strong interest in the materials community regarding the so-called 2D or low-dimensional crystals. These are crystal systems that can be exfoliated into basically 2D or quasi-2D atomic sheets, you know. And because of their 2D geometry, they have very exotic and different properties with respect to traditional standard crystals that are periodic in all three directions. In particular, we will see that the interaction between electron and holes in these systems is much, much stronger and cannot be ignored, and DFT cannot describe it. And electronic excitations here will form bound states that we call excitons, and this we will see later. Another thing that you can do here is that actually you can engineer, you know, artificial structures by putting together these 2D systems, and in this way you have extreme control on the electronic properties of the heterostructures that you build in this way. And these type of systems are extremely relevant for so-called optoelectronics, which is where you modify, for example, the electronic properties of a system through light-matter interaction. And for this, we have to go beyond DFT. Then another case, a specific case, would be, for application, would be photovoltaics, right? One possible process related to absorption is that part of the light that is absorbed by the crystal, so the energy that goes inside the crystal, is converted, if you apply a potential, to a current, right? And there's a lot of interest in this, of course, and there's a lot of computational interest. And this is a very new material that actually we are studying right now on Fugaku as part of the Anami project. It's called a perovskite. Perovskite is not really new. You can recognize it because they form these octahedral bonds. But in reality, this is pretty weird because you have like a 2D perovskite, you know, connected by these organic molecules. And this is supposed to be pretty promising for stability at room temperature and also high efficiency in photovoltaics. But this is a very large system, right? So this system or similars. These are very large system, and we need to do HPC in order to study those. Okay, so what happens? Well, how can we do this? We have to pass from the macroscopic picture, or just a piece of matter, and electromagnetic waves that enter it, to the microscopic picture. Of course, we will do this in a very hand-wavy way, but I hope to give at least the idea of how we do this. So here we have on the left side a piece of vacuum and an electromagnetic wave that is oscillating and traveling through it. Right? And on the right side, it enters inside a matter system. And what happens, you know this for sure, it gets attenuated. No? It gets exponentially attenuated. And we can describe this with Maxwell's equation, for example, right? So we make some assumption that the material is isotropic, homogeneous, and non-magnetic to simplify everything. And then on this side, we have the simplest possible form of Maxwell's equations for the electric and magnetic fields. where there are no sources of the fields, no charges, no currents here. It's just vacuum and the wave propagating, so everything is homogeneous. But on the side of the system, there is an electron density which is charged, so it is modified by the fact that these fields enter the material. And so the Maxwell equation here acquire some source terms, an induced current and induced charge. And you see here, they acquire also this epsilon, which will be extremely important. This is the dielectric function. It is a complex function. It has a real and imaginary part. And we will flesh this out when we go. So we can solve this, okay? The vacuum part, this is the homogeneous part, just gives rise to the wave equation. And the solution, that's what I said before, is just a plane wave, right? That travels to the vacuum unopposed, let's say. And the intensity is just given to the initial intensity. But then if we solve the inhomogeneous equations, so now the inhomogeneous wave equation is this, and you see that we have this sigma appearing. This is the conductivity. But in reality, the conductivity, you can rewrite it in terms of the dielectric function. So it's always the same function, basically. Okay, we solve this, and what do we get as a solution? It's not a plane wave, for sure. It is this. So we have a kind of plane wave part, you see, e to the I, so oscillating sinusoidally, with this n. This is the refractive index. Seems something different, but in reality, is always related to the dielectric function. So it's always a dielectric function. And the difference between this and this is that the momentum, the wave vector of the light here is different. And basically this means that the light inside the medium travels at a different speed. Not the speed of light, but c divided by n1. This is known. But then we have a second part of the solution, which is a real exponential, depending on the imaginary part of the refractive index, which is connected to the dielectric function. And it is this part, the most important part, that gives the attenuation of the wave inside the system. In fact, if we calculate the intensity now, this part does not go to 1, and we can lump all this stuff into one single function called alpha, and you see that we have exponential attenuation. This alpha is called the absorption coefficient, right? And gives exactly the exponential attenuation. This is the intensity of the wave inside the system. Again, we can rewrite this to emphasize that it mostly depends on the dielectric function, and in particular on the imaginary part of the dielectric function, which is the quantity that we are going to want to compute. Okay, but Maxwell's equation, they don't give us any prescription on the form of this. We don't know which function to plug here. We can use models, of course, but we know that the shape of this, the form of this, is basically dictated by the underlying microscopic crystal structure and electronic structure of the material. So now we have to leave for a short while the macroscopic world and go into the microscopic regime, and this is where many-body quantum mechanics will come in. Okay. Now, the next part will be a bit technical. Of course, you don't have to memorize the equations, okay? Just to have like an idea, an intuitive idea of what is going on, okay? So we go to the microscopic scale, and now the system is not anymore homogeneous. Before I took the assumption, okay, the system is homogeneous, but it's not. At least it is not in the scale of a few angstrom, which is the lattice constants of the crystals. It's not homogeneous, of course, because it's a crystal. And so it means that microscopically, the dielectric function depends on the position. It non-locally depends on two positions. Okay, but even if the system is not homogeneous, at least it is periodic. So it is an infinite repetition of this unit cell forever, right? This is called monolayer boron nitride. It's very similar to graphene. As you can see, you just have two different atoms. Okay, so since it is periodic, we can take a Fourier transform, of course. And this is what we do. And we go from real space to reciprocal space. And also in reciprocal space, we have a unit cell, which is different, and which is repeated forever. And then we sample this unit cell with wave vector points. These are the grids where we calculate stuff. our functions are defined over these grids, and we calculate it. And then the denser the grid, the accurate will be our function, our final calculation of the function. So, since the system is periodic, even though in principle the electric function depends on two momenta, as it depends on two positions, in reality, we can make it in a tensor form in which for each couple of repeated unit cells, there will be a function that it just depends on the momenta inside the let's say a single unit cell, so because this is repeated everywhere, right? So we can write it as a tensor, and this will simplify many things. So this is the explanation why sometimes you see this epsilon GG prime, what it is. It's just that big Q is Q plus G, and big Q prime is Q plus G prime. It's just a matter of rewriting. It's nothing particularly crazy. Okay. Now, the microscopic form of the electric function. Well, the electric function is defined, okay, as the variation of the total potential inside the material with respect to the external potential, which is the laser field that is coming in, okay? The total potential is the laser field plus the induced potential from the polarization of the charge inside the system. We can actually rewrite this in such a way that we make sure we understand that the only thing that really matters is the variation of the electronic density, which is being polarized, with respect to the external field. And this quantity is the main quantity of many-body perturbation theory. Basically, it's called the response function, or in this case, a susceptibility. Okay. And for the sake of simplicity, we will make a slight redefinition of the susceptibility. This is what you find in textbooks. We will use this one, that is the variation of the electronic density with respect to all macroscopic field, both external and induced. You don't have to worry too much about this. Let's just say they are equivalent up to a certain point. Okay. Now the problem, we are pushing the problem away, no? Now we push the problem from epsilon to, okay, what is this? We have to compute this. So this, we call this chi, typically, the response function. And this is just the Coulomb potential in reciprocal space, it's just a formula. So we want to compute the full of this, but we have to know this. Now, the first thing we can do, of course, we are in quantum mechanics, we are in periodic systems, we are in DFT. We can rewrite the response function chi in a different basis. Not anymore the basis of so-called plane waves, so the G vectors, but the basis of electron-hole transitions, what we said before. So now, a response function written in this basis just basically couples electron-hole transitions from a valence band at k point k to a conduction band at k point k prime. And the difference between the two is Q, which is the momentum carried by the incoming electromagnetic wave, okay? Okay, so now we have some coefficients, no? We have this change of basis, and then we have the chi, the response function, on a different basis. Now there is a simplification that we can make, because we are considering optical absorption, so there is optical light. Optical light has a wavelength, and this wavelength is much, much larger than the microscopic scale, the microscopic repetition unit of the crystal. So yes, the wave formally varies in a sinusoidal way, but in reality, as far as the crystal is concerned, you see we have one or more order of magnitudes of difference. So we can make the approximation that actually it's almost constant over the length of a lattice unit cell. And this leads to the so-called dipole approximation, where the oscillating exponential of the wave is just approximated to 1 plus first order, right? And if we do this, basically we can extract the Q vectors from the original coefficients, and we expose this D. These are the so-called dipole matrix elements. This basically is the strength of the coupling between electrons and light. And this is a quantity that we can compute with first principles codes, right? So this is the first thing that we can directly compute. Okay. So now we have this simplification. Also those Q that came out nicely eliminate the divergence 1 over Q square. And we have this, but still we don't know what is this, right? Okay, so Actually, these can be written in different ways. Why? Because it depends on the approximation that we want to make in the descriptions of the underlying electronic system. Daniele already told you that here we decide which approximation to do for a very complex theory. And different levels of approximation may be useful for different observables, which may be described well, maybe the lower level approximation, or sometimes not, and then you have to go to the next level of approximation. And so we have several levels of chi that we can think we compute. And the simplest possible one is the level of independent particles, which is effectively the DFT con-sham level, because you have effectively non-interacting particles. So we take the DFT Hamiltonian, the one that come out from DFT code, like quantum espresso, ABINIT, and so on, VASP. And then we perturb it with our external laser field. And then you can show, with many-body perturbation theory, then the response function is simply given by this expression. Its main feature is that it's already diagonal in this basis that we chose before. So you don't have a double sum because it's diagonal. Therefore, your expression just becomes this one. So if you studied a little bit of perturbation theory, you know this is just Fermi golden rule from first order time-dependent perturbation theory. So you can already arrive at this expression also in that way, for example. Reminder, what we want, we are computing this, which is the absorption strength. We are computing this, and this is this. That at this level of approximation of non-interacting electron and holes is given by this simple expression. This quantity we compute with DFT, with DFT quantities. These we can compute with DFT or also with GW, and that's what we need, energies and electron-light coupling matrix elements. Okay. Now we want to add a little bit of electron-electron interaction, right? So electrons are charged particles. We should consider that they interact with each other. So let's go a little bit to a better approximations. Yeah, okay, nice. Okay, so this is the one that we have already checked. Then we can decide that we also consider the variation due to the external field of the classical part of the electron-electron interaction. You can divide the electron-electron interaction in a classical and quantum part, as is usually done. If we only consider the classical part, which is called the Hartree potential, then we have this modified Hamiltonian with the variation also of the Hartree potential that depends on the variation of the density that depends on the external field. Or we can do even more, and we can go to the same level of approximation that Daniele explained before regarding the GW quasi-particle corrections. If we want to go to a consistent level of approximation as GW for absorption, it's not enough to use this. We also have to add the GW, the screened electron-electron interaction, which is this one. So you see there is another term that gives you how the screened electron-electron interaction varies because we have an external field. Okay. By the way, in order to calculate this, you need this, right? So you use this approximation to get the microscopic epsilon, okay? From this approximation, you need to put the here to get this approximation. And then now we use this approximation to calculate another epsilon. And this will be the final level at the macroscopic level that will give absorption, including all these effects. And these are the effects that we need to describe, for example, optical spectra in 2D systems or in strange systems as I will show you. Okay. Perfect. Now we have a problem, though. If we do many-body perturbation theory, we find that the form of the response function is a little bit more involved because now you have these new terms that come from these two additions to the Hamiltonian that are not diagonal in the single particle, in the transition basis, let's say. So also the chi is not diagonal. And now here we start talking about diagonalization. So we need to find a form in which this is diagonal. If we find it, then we can also switch this to a basis in which is diagonal. So formally, we can think that we write this. We find a diagonal form for this. We change the basis from the non-diagonal, the one in which it is not diagonal, to the one in which it is diagonal. And we redefine the dipoles, including this basis change. And then these will be our final expression, right? Great. And so then it will be quite simple, let's say, because we can write it like this, but we still have to know what is this. Finally, assuming that we can diagonalize it, the expression will become like this. So again, very simple. And we have the final expression for absorption when we include electron-hole interaction and the maximum approximation that is used normally, which is able to capture electron-hole bound states that, as I said before, typically they're called excitons. Okay, so this will be our final expression. And all this flow of stuff typically is called Bethe-Salpeter calculations, Bethe-Salpeter equation. Technically, a version of the Bethe-Salpeter equation is this one, if you want. It's a type of Dyson equation involving the response functions, basically. Okay, finally, we have finished. These quantities, the purple quantities, are those that we can finally compute with a many-body code, such as Yambo, for example. And how do we do that? Basically, we recast the susceptibility into this formal expression. And you see that now we construct an effective matrix, an effective Hamiltonian. And it is this that we will diagonalize. And the eigenvalues of this will give us the excitation energies. And the eigenvectors of this will give us the coefficients that we need to properly compute this modulus square Fermi-Golden rule expression. Okay, so all the problem that we discussed before is now compressed into, if we can just diagonalize this matrix, okay? Then we have everything that we want. What do we get then? Well, this is a calculation of the optical absorption spectrum in the independent particle approximation, so it's the first one that I showed with no electron-hole interaction. Again, for the system that we are using as example, which is monolayer hexagonal boron nitride, which is this one. So here what we are describing, as I said before, we are describing the transitions from valence to conduction because of absorption of a photon. And so as you can see from the equation, the optical absorption spectrum will start around 7.3, which is this energy difference, the band gap energy of the material, where absorption can start because you have electronic states to go to, and then we'll continue with all the other possible states that can be reached if you increase the energy of the laser, right? And by the way, this quantity, calculation of this quantity involves the electronic wave function. As you can see, of course, they are periodic functions. So these are related to the density of holes in the bottom and the electrons in the top of this material is periodic over the crystal lattice, right? Okay, but this is completely wrong and describes nothing, it's garbage. Instead, if we switch to the Bethe-Salpeter equation, we find not just a small correction. I chose, of course, the most extreme case, and normally it's not so extreme. But just to see, a result that is more in line with the experimental real results is completely different, completely from just DFT or even GW on top calculations. And what is happening here is that we have a system that is almost unscreened because it's a plane of atoms. So the interaction between a hole and an electron, probably I can show from here, is basically unscreened. And since it is unscreened, the W term, which is responsible for the binding of electrons and holes, is strong, super strong. It is so strong that it creates bound pairs 2 electron volts below what should be the band gap for electronic photoemission. And as you can see, I go back a little bit, we can also see how these peaks are originating from a linear combination of all possible transitions. In this case, I'm analyzing this, the main peak, and it basically comes from a linear combination of all the possible dipoles where the A's are non-zero, which is just this area, right? Okay. And the wave function now is very different. If we fix the hole on the nitrogen, then the resulting electron density is basically around the hole in the vicinity of that particular, of where the hole is. Okay. Okay, so this is basically what you can calculate. And probably I have some examples. Yes. So this figure was hinted at by Daniele before. This is just silicon, okay? It's the simplest system possible. And you would argue, okay, it's also the simplest to simulate. But if I want to find the optical absorption on silicon, so the red dots are the experiment. Okay, I do a DFT calculation, even to the level of approximation in which you include the variation of the classical part of the interaction, which is the blue curve. Yeah, nothing is going on. Okay, maybe I didn't do the GW, no? I didn't correct the band cap. Okay, then I get the purple, completely wrong. Instead, the correct shape, to a degree of numerical approximation, is given if we include the full solution of the Bethe-Salpeter equation. And this was shown, I think, first by Francesco T in 2003. And another example is here. This is a very famous material in the community. Is molybdenum disulfide monolayer. Is the most famous example of this class of materials called transition metal-like chalcogenides, which are, okay, extremely useful for many, many things. And you see here the absorption spectrum has a particular feature of having two peaks. And these are two excitons that are below the band gap, the quasi-particle band gap of the system. The splitting of these two excitons is given by an interaction that is called the spin-orbit interaction. And the only way to capture it correctly is to solve the Bethe-Salpeter equation, as it has been done here. Okay. Now, we go back to the problem of before. We need to diagonalize this. Pretty easy, no? Pretty easy task. So this is the form of the excitonic Hamiltonian. We have a diagonal part that is just the difference in energies, the electron-hole transitions, here at the GW level, right? And then we have an off-diagonal, well, diagonal, but also off-diagonal kernel, which is given by the electron-electron interaction at the level that we are describing it. So the calculation flow will be like this, no? We do maybe a GW calculation, we first compute the static screening, then we build the kernel, this we will do in the tutorial. And then from the kernel, we diagonalize all of this, and finally, we obtain the epsilon, okay? Which then the imaginary part gives the absorption. Or instead, the imaginary part of the inverse gives electron energy loss spectra, for example. Very good. Let's now analyze a little bit more in detail. Let's go. No. Okay. Let's analyze a little bit more in detail these matrix elements. You see that we have basically three different types. We have the type of elements that couple transitions with positive energy from valence to conduction to valence to conduction. We have those that couple transitions with negative energies, and then those that couple transition with positive and negative energies together. So this creates 4 blocks, you know, in our matrix, which are represented here. So this is like the so-called resonant part, where energy is positive from valence to conduction, from valence to conduction. Anti-resonant, where energy is negative from conduction to valence, from conduction to valence. And then the coupling parts. One interesting thing is that this matrix is not Hermitian. It's actually pseudo-Hermitian, which basically, in this case, means that the eigenvalues are still real. But the left and right eigenvectors are not, let's say, they are not Hermitian, they're not orthogonal, and they're not the conjugate transpose of each other. The full matrix, okay? But many times, in many semiconductor systems, actually these terms are pretty small, and you can neglect them. And then you reduce all these blocks to just this resonant block, which is fully Hermitian, okay? And also much smaller. Okay, so how easy it is to do this? Let's see some examples. Let's consider the simplest system that I showed in the example, monolayer HBN. Then if we do just the resonant part, basically more or less the dimension of the matrix will be 15 megabytes, I don't know. If we include the full coupling pseudo-Hermitian case, 50. We go to monolayer MOS2, the other calculation that I have shown. This has more atoms in the repetition unit cell, and many more electrons that are relevant for optics in those atoms. And this is the reason why, in the end, it is much larger. So it's 400 MB only the resonant, and then breaks 1 gigabyte size if you do the full. What if we consider the bulk case? So we take one layer of MOS2, we put another, and then repeat it to infinite. This is useful for several applications, and in some of these, you have to consider the full matrix, full pseudo-Hermitian matrix. You see, we already want to load and diagonalize 40 gigabytes. What if we go to even larger systems? For example, titania, TiO2 anatase phase. Even in the resonant case, we already have 300 gigabytes of matrix, okay? And then if you add defects, if you add atoms, it becomes larger and larger. So this is to show that typically this type of calculations are limited by memory constraints, not really by time to compute, especially on GPU. That is not really the problem. The problem is, can I load so much? No? And this is what we want to solve, basically. Okay. And this is the last slide, just what strategies we use up to now for diagonalization of this matrix. So we have Hermitian and pseudo-Hermitian case, but also you have to, of course, consider different cases for CPU cluster, like Fugaku now, and GPU cluster, like Fugaku Next or the European clusters. And well, for the Hermitian case, obviously we use LAPACK and SCALAPACK for if you want to diagonalize the full matrix. But often we don't need to do that. We can just iteratively diagonalize, iteratively find only few eigenvalues, And for this, we have an in-house solver. It's called the ADOC solver based on the Lanczos algorithm of continued fraction, which is actually the fastest that we have, but only gives access to the optical spectra. So you get the absorption spectrum, good, but you don't get eigenvalues and eigenvectors that actually are needed for many applications and for many physical insights. Then we can also have iterative methods that also give access to eigenvalues and eigenvectors. The one that is currently implemented and working, and also is the suggested basically, is a SLEP-C. But also I think they are working within the Anami projects on the Chase library. Okay. Then if we go on GPU, of course you have to use GPU-based libraries. So there are the NVIDIA ones, QSolver and the parallelized QSolver MP, which I'm not sure it performs so well, I don't know. Then we have the very, very badly, nice. Then there is the Magma, that is basically done by the same people of LAPACK, but it's GPU. Then we are working on the ELPA library for the full diagonalization. And then we have the iterative method, so Lanczos ADOC is ported on GPU, SLEP-C works on GPU, and Chase in principle will also work on GPU. What if we go to the pseudo-Hermitian? Well, on CPU, the situation is really good. Of course, if you want to do the full diagonalization, which is not suggested, there is only LAPACK with a generic routine that does not take into account the fact that the matrix is pseudo-Hermitian. It's just general for any non-Hermitian, so it's maybe not the best. Iterative only spectra works, and SLEP-C for also eigenvalues and eigenvectors, iterative also works. GPU-K pseudo-Hermitian, don't do it, but if you really, really need to do it, there is still Magma that works. And then all these others are in orange because we are still, I don't know if we are released properly, and some are in the testing phase. So hopefully in the future, all these, or even more, I don't know, will be available as strategies to diagonalize the matrix that, of course, you have to decide what is best depending on your system, or the specifics of what you want to calculate and of the machine that you have. Okay, so that was the last slide, I think, I hope, yes. We have just the conclusion. Let me just walk to the main points that should be, kept in mind. So optical absorption is a spectroscopy technique that probes the so-called neutral excitation. So it's not when you put a new electron in the system, altering the charge, or you remove one, altering the charge. It's just an electronal transition that does not alter the charge. And these are called neutral excitations. Typically, for most systems of interest nowadays, it requires post-DFT methods because you have excitons, electronal bound states that are due to microscopic details of electronal interactions that are not described by DFT. Okay. And basically all implementations, not just in YAMBO, reduce these to diagonalizing an effective two-particle Hamiltonian. the Bethe-Salpeter Hamiltonian to particles Hamiltonian is called in different ways. And we are working on efficient implementations in order to continuously be efficient in solving these, especially in view of the fastly changing technological landscape of HPC systems. And with this, I just thank to the sponsor, Max, as Daniele said, also Italian sponsor, in particular the ANAMI, bilateral collaboration between EU and Japan, which is the reason why we were able to come. And thank you for your attention.